In orthorhombic steel deck, the transverse distribution of wheel loads generates high local stresses in the small thickness of the steel members. In order to reduce the stress level and thereby extend the fatigue life, a strengthening technique with the overlay UHPFRC ultra-high performance fiber reinforced concrete were proposed and commonly used based on the experimental studies. In this study, three-dimensional finite element analysis with the nonlinear constitutive material models is performed to investigate the beneficial effects of the USB-RYC overlay in the composite deck. My name is Ma, a graduate student of the Laboratories of Bridges and Structural Design Engineering from Hokkaido University. This is the contents of the presentations. The first is the introductions of the research. The second is the analytical models, including the details of geometry, the boundary conditions of the composite deck, as well as the nonlinear material models of steel and USB RCs. The third is the static results of the deflections and strains at the critical locations in the steel bridge deck. And final section is the conclusions on the beneficial effects of using the USB RC overlay in the bridge deck structure. Introduction of research. Orthotropic steel bridge deck has been widely used in many large span bridges due to its lightweight and convenient in construction process. However, in recent years, the fatigue cracks have been reported in the welding connection parts in the structure. Fatigue may occur when a member is subjected to repetitive cyclic loading even below the static strain level. According to the Paris law, crack propagation is dependent on the stress rate. Therefore, it is significant to develop the strengthening technique that can effectively extend the fatigue life of the bridges using OAT structure. One promising technique that is appropriate for both the new and existing bridges is to overlay the high-performance cementitious materials such as steel fibers reinforced concrete (SFRC), engineered cementitious composite (ECC), and ultra-high-performance concrete (UHPC) on top surface of the steel bridge deck to improve the fatigue-resistant capability of the structure. It has been found that the stiffness of the bridge deck has been enhanced via the significant reductions in stress level and range at the critical locations in the steel members. Comparing to the conventional high-performance cemented material, ultra-high-performance fiber reinforced concrete (UHPFRC) exhibits more excellent properties such as very high strength under both tension and compressions, as well as the strain hardening behavior in tensions that is expected to improve the overall stiffness by reducing the stress level in the steel bridge deck. Moreover, a highly dense matrix of UHPFRC provides the material an extremely low permeability, which means the UHPFRC overlay can work as an erosion protection layer to severe factors such as water and chloride ion. In this study, a nonlinear finite element analysis is performed by using the commercial FEM software MSCMark to simulate the steel bridge deck with and without the USB-RC reinforced overlay under static wheel load. The strengthening effect of the USB-RC overlays is investigated based on the deflection of the steel deck in both longitudinal and transverse directions and the deformations at the position under severe stress concentration. The analytical results are compared with those from this experiment of the wheel load acting on the steel deck associated with the overlay USB RC that were conducted by the J-Tipcom Construction Association. The following sections is the analytical models developed in this study. The descriptions of the material models for steel and USB RCs, as well as the geometric detail and the boundary conditions of the composite deck, are presented in this session. Finite element modeling. The commercial finite element software MSC Mark is employed to simulate the overlay USB RC strengthened OSD under static wheel load with user material subroutine. Geometric detail of composite deck. These figures show a steel deck with a span of 3,300 mm and 2,720 mm along the longitudinal and transverse directions. The strengthened bridge deck is composed of the USB RC overlay, the steel deck plates, the mount girders, the cross beam, and longitudinal open pub ribs. Along the transverse directions, the steel deck is supported by three cross beams with a spacing of 1,500 mm. Along the longitudinal directions, the steel deck is supported by two mount girders and seven pub ribs with a spacing of 320 mm. The steel deck plates with a thickness of 12 mm is overlaid by a layer of USB RC with a thickness of 25 mm. As shown in the mesh pattern, the 3D Ace Node solid elements is selected for modeling of the steel deck plates and USB RC overlay. The USB RC overlay is divided into three layers in the vertical directions. To reduce the computational cost, the four node thick cell elements with a thickness assigned in the marked geometric property options is used to simulate the width and length of the main girders, cross beam, and longitudinal bob ribs instead of the 3D solid element. The thickness of the shell elements assigned for the bob rib in the finite element models is chosen with the identical cross-sectional areas to the actual one. Boundary conditions. The four edges under the flanks of main girders are simply supported on the 3000 mm span in longitudinal directions. The two edges from the east side are constrained in all three translational directions. The other edges are restricted from the translation in x and y directions, as shown in this figure. The length pattern of the wheel load is simulated as two paths along the longitudinal directions. The distance between two loading paths, representing the gap between the two rubber ties, is set as 110 mm in the middle of the transverse side. For the static analysis, three uniformly distributed loads, which are named as log west, log east, and log centers, as shown in the figures, are located in the logging lane. Acting on the area of 220 mm multiplied by 250 mm, which is assumed as the rubber tie contact area. The static load level is assigned to be 100 kN, referring to the experimental design. Material model. The stress-strain response of steel material in the analysis is shown in this figure. Steel is assumed as an elastic, perfectly plastic material with a yield stress of 280 MPa. The yield criterion in the model is following the von Mises law. The Poisson ratio and elastic modulus of steel material are 0.3 and 200 GPa respectively. Material model of UHPFRC. The stress-strain relation of UHPFRC in both compression and tension are shown in the figure. Constitutive law and rocking behavior of UHPFRC are coded using Fortran Ramin language. Under tensile loading, the typical behavior of UHPFRC are exhibited by three domains: elastic, strain hardening, and strain softening. The rocking strain and tensile strain are chosen as 6 MPa and 9 MPa respectively. The maximum tensile strain for the strain hardening domain is 1750 micro. With this state, the multiple microcracks start to form and propagate stably. Beyond the ultimate tensile strain, the macrocrack initiate at the strain softening domain, and UHPFRC finally follow at the end of this phase, with the ultimate crack width equal to 6 mm chosen by half of fiber length. Under compressive loading, the stress-strain law of UHPFRC is exhibited by a bilinear relation with a compressive strain of 133 MPa. The Poisson ratio and elastic modulus of 0.22 and 31.3 GPa are used for UHPFRC in this study. Racking behavior in USBRC. The multiple fixed rack model is used to represent the rack formation and propagation in USBRC under tension. Rack initiate when the maximum principal strain exceeds the racking strain in the direction perpendicular to the principal strain. Similarly, the second and the third rack initiate perpendicular to the first rack when the second and third component of principal strain reach the cracking strain. The total strain of racking material is decomposed into rack component and non-rack component in this approach. The global increasement stress strain were then obtained by rod and Lowen rods as follows, where delta sigma and delta epsilon are the global increasement stress and strain vector. DCO and DCR are the strip knot matrix for the non-rack and rack component. Hence is the transformation matrix reflecting the orientation of the rack. In this session, the static results of deflection and strain at the critical locations under steel deck plates as well as the middle crossbeam are considered in the models with and without USB FRC layer to investigate the beneficial effect of the strengthening overlay in the steel bridge decks. The influence of the overlay's USB FRC thickness is also examined in this session. Firstly, the deflection of the bridge slab is examined under the steel deck plate. The results are obtained along the path WE and path SN as shown in the left figure. From the displacement curves along path WE under the log east condition in the right figure, it can be seen that there still exists large variance in the calculated displacement. The reason is that in the experiment, there is a steel beam system supporting the main girders of the steel bridge deck, and the displacement data from the bottom of the steel deck are collected by the LVDT measurements which are placed on the supporting girders. Under the wheel load, the supporting girder has been deformed in vertical direction combining with the other deformations from the connections of the supporting steel members. This leads to the higher values of displacement data from the experiment to the analytical model. From FEM model, the analytical results are only verified based on the trendy arrangement in the displacement distributions with the experimental data points. From the displacement curves along both the path WE and path SN, it can be seen that the analytical results from the model with and without the overlay USB FRC exhibit similar tendency with the data from the experiment for both longitudinal and transverse direction. AC also found that the maximum deflection of the steel deck plates occurs under the east load. Considering two analytical models of the steel deck, the deflection behavior is obviously improved after applying the USB FRC overlay, especially in the contact region of the wheel load. The stiffness of the strengthened composite structure has been increased by the efficiency in mass transfer resistance of the USB FRC layer. The percentage of change in deflection of steel deck with the USB FRC overlay is approximately 51% less than the original one without the strengthening part. Following the deflection results, the strain data on the bottom of steel deck plates are also investigated. The right figure shows the transverse strain distribution on the log east along path SN where the strain gauge are located. It can be observed that the analytical curves show an acceptable adjustment to the experimental data, except for the strain results at SEL1 for the model without USB FRC. This may be because the mass at the local region above the middle stiffener is not fine enough to capture the strain behavior at SEL1. The second reason is that the contact region of the rubber ties used in the models is not exactly the same to the real contact area in the experiment. From these figures, it is obvious that the strain level and strain drain in the steel deck model reduced with the existing of USB FRC overlay. The strain reduction rates in the steel deck at the critical location at the middle of SN line reached approximately 83% from the analytical models applying the strengthening overlay. From the literature, the rib to deck weld joint and the edge of circular shape cutout are the critical locations under severe stress concentration in the steel bridge deck. Therefore, the strain results at these locations are also examined along part U and part L in the middle cross beam as shown in the left figure. The U and L part are divided into 3 and 4 intervals with a sublength of 270 mm and 220 mm respectively. The right figure shows the vertical strain distribution under log east along part L. It is found that most of the strain curves very well with the experimental data points. It can be seen that the strain distribution along path L changes sharply when they approach the edge of the circular cutout in the middle crossbeam, and the higher strain level are obtained from the first left cutout part. Similar to the strain result along path L, the strain level along path U near the rib to deck weld joint significantly increase when the strain curve approaches the cutout edge. The highest magnitude of strain is also obtained from the first left cutout. From the strain distribution along path U and L, it can be seen that the strain level as well as the strain range in the model with UHPFRC are smaller than those from the model without the strengthening layer. Thus demonstrates the increase in overall stiffness of the steel bridge deck reinforced by the UHPFRC. For middle cross beam, strain decrease at a critical location in part U is about 4%. The influence of USB-FRC overlay thickness in the reduction rates at critical values of deflection and strain obtained from the path SN are also investigated and shown in this figure. The thicknesses of USB-FRC layers chosen for the parametric study are 25, 35, and 50 mm. As can be seen from the figures, the percentage of reduction in deflections and strain values linearly increase with the thickness of the USB-FRC overlay. For the model of 25 mm USB-FRC thickness under the load level of 100 kN, there are only few crack elements on the top surface of USB-FRC. For the model with 35 and 50 mm of USB-FRC thickness, there is no occurrence of crack in the overlay. Therefore, the linear variations of the reduction rates are obtained. Consider the strain reduction rates along the midspan. The value in S direction or transverse directions are always higher than those from the vertical and longitudinal directions. It means that the stiffening effect of USB-FRC overlays is dominant in the transverse directions. Conclusions. In this study, the strengthening effect of the USB-FRC overlay on the steel bridge deck is investigated by means of finite element analysis. The radical deflection under static wheel load reduced until 51% for the USB-FRC layer thickness of 25 mm. The reductions in maximum strain at the bottom of steel deck and the deck plate cross beam welded connections has been calculated to be about 33% and 4% respectively. The contribution of USB-FRC overlay in OSD strengthening becomes more apparent with the increase in the USB-FRC thickness, as found in the parametric study. With the beneficial effect in enhancing the strength and stiffness of the OSD, the USB-FRC overlay can be applied to extend the fatigue life of the steel bridge structure subjected to high traffic loading. Thank you very much for your kind attention.